So here is an interesting question. How do we connect the linear variables with the angular variables? We already talked about how there's a link between them. There's an analogy between them, right? But can they be connected? So for example, let's say that I have, as is in the slide, connecting linear and angular variables. Let's say I have a helicopter blade, okay? And I know that this helicopter blade turns through a certain number of radians from here to here, okay? Can I find out how far, right, the linear distance, this point moved from here to here in meters, okay? And the answer is yes, you totally can. In fact, this is something many of you maybe learned in high school or middle school, that the arc length, right, of any part of a circle is equal to the number of radians that you move through times the radius that arc has. So this totally makes sense because obviously the bigger the radius, right, the more that point is going to move through. So this point here is going to move through much greater distance than this point here, let's say, right? This arc length is obviously much less than this. So the bigger the r, right, the farther you are out from the axis of rotation, right, the more distance you're actually moving through. Okay? Does that make sense? So let's take an example of like a helicopter blade that's the size of the whole United States of America. In fact, let's say we put the middle of the blade like right in Denver, Colorado, okay? And then the blade swings all the way out to San Francisco on one end and then Washington, D.C. on the other end, right? Imagine then that goes through a pi/2 rotation, right? The distance that the point at the end of that helicopter blade would move would be thousands of miles, right? It would like swing up through Canada, right? But then imagine a point that's like right next to me. So I'm in Denver and I'm looking at this point, and this point swings through pi/2 radians. That's like not even a meter, right? So the farther you are out, the more distance you cover, okay? And that means that the farther you are out, the faster you're going to be too. So actually, this should be v. So if this is the arc length, or the length that the point is moving through in meters, right, then the velocity of that point, right, would have to be equal to omega times r, which also makes sense because this point, right, the bigger you are, the farther you are out, right, the faster you need to go to cover that distance in the same amount of time. So this velocity should be higher as r is higher, right? This guy here is going to cover is going to move through much more distance in the same amount of points, in the same amount of time that this point is going to move through if it rotates from here to here, right? So here you'll have a big distance divided by time, and here you'll have a small distance divided by time. So the bigger r is, the faster the point needs to go in order to make that same motion in the same amount of time, okay? And it's not much of a surprise that acceleration works the same way, that there's this relationship between the linear acceleration is equal to the rotational acceleration times r, okay? So basically, r here is the key to translating between the linear world and the rotational world, okay? So if you take all of your rotational variables and multiply by r, you get back your linear variables, all right? How does this work? Well, let's do an example. The next slide really just has what I already have here, okay? How you get your linear variables by multiplying by your rotational variables. And so let's take a look at this misconception question, number 1 then. It says Bonnie sits on the outer rim. Here's a merry-go-round. Okay, so we have Bonnie sitting on the outer rim. This is B over here. And we have Jill sitting halfway in between. Okay, and they're all rotating this way. So the merry-go-round makes one complete revolution every 2 seconds. Jill's linear velocity should be what compared to Bonnie's? Well, Bonnie's is a full R, right? Jill's is R over 2, right? So if we want to find out the linear velocity of Jill relative to Bonnie, then we have to just take, if this is Bonnie's, right, velocity, then we just have to divide by 2 by R to get Jill's velocity. What is that? It's going to be the velocity divided by 2, right? So Jill's velocity should be half of Bonnie's velocity, okay? If we're dividing by R, we must divide by V, so Jill will be going half as fast in the linear world, right, in actual meters that's moved, right? And Bonnie will be going twice as fast as Jill because her radius is twice as long as Jill's radius, okay? Let's look at the rotation of a bacterial flagella, okay? It says that some bacteria are propelled by biological motors. This is really, really cool. Another example of how life has just developed the funnest little tricks to get it to survive and basically just employs physics, uses physics to make things happen, okay? So some bacteria are propelled by biological motors that spin hair-like flagella. A typical bacterial motor turns at a constant angular velocity and has a radius of 1.5 times 10 to the minus 8 and a tangential speed at the rim of 2.3 times 10 to the minus 5. What is the angular speed or the magnitude of the angular velocity of this bacterial motor? Okay? So, well, let's just use the classic equation. We know that V equals omega R, right? Which means that the rotational speed should be the linear speed divided by R, right? I'm just dividing both sides by R there, right? And it tells us that the tangential speed at the rim is 2.3 times 10 to the minus 5, right? And that it tells us that the angle, that the radius, right, of that rotating flagella, right, the radius of it is 1.5 times 10 to the minus 8 meters. That's meters per second there. So the angular speed, in other words, the number of radians per second that flagella is spinning at must be, I am getting over here, 1,533 radians per second. That's fast. So not only can biology use physics for its own benefit, but it does so in really remarkable ways. That's a lot of radians every second that these things are spinning in order to propel this bacteria. Okay. Next question. How long would it take the motor to make one full revolution? Okay. Well, this is another case where we don't have any acceleration. They're not talking about acceleration, right? So we can just use the relationship that omega is equal to theta divided by time, right? Which means that t is really equal to theta divided by omega. Okay, so one revolution, as we know, is 2 pi radians, right? And we know that the angular speed is 1533. So it should take just a tiny fraction of a second, 4 milliseconds, to make one full revolution. Again, remarkable. Life's really cool how it works. Okay. Last problem for looking at this conversion between linear and angular variables. I think this is a really fun one, and it's the question of the Tower of Pisa falling, right? Because it's not just stuck at an angle. This thing continues to fall a tiny, 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 tiny bit every single year, and we're going to look at that right now. Okay, so I have a Tower of Pisa. So it says between 1911 and 1990, the top of the tower of the Leaning Bell Tower at Pisa moved toward the south at an average rate of 1.2 millimeters per year. The tower is 55 meters tall. So let's take a look at this guy here. Right, there is the Leaning Tower of Pisa, right? And so between 1911, so we'll say this is 1911, and 1990, it actually tilted a little more, rotated a little bit, right? So this is 1990. Okay? And it has been rotating, and so, it would continue to rotate until it hit the ground, right? So the speed, the rate at which it rotated, it says is, well, this is going to be actually, because it's in meters, this is going to be a linear speed. So V is equal to 1.2 millimeters per year. Cool, huh? Cool that we can actually measure that. That's obviously nothing. 1.2 millimeters, that's like, you know, the tiniest little fraction of like a little yardstick, right? That's tiny, tiny little millimeter every year. But we actually can pay attention to how much it moves because between 1911 to 1990, that's kind of significant. And because it is a preserved heritage site, we are keeping very close eyes on it, okay? Also, this is 55 meters tall. So that tells us that the radius is 55 meters, okay? In radians per second, what is the average angular speed of the top of the tower's top about its base? In other words, at what rate is this angle changing? Okay, so we want to find this omega in radians per second. What is that? Okay, all right. Well, first thing we need to do, okay, is I would want to turn that into SI units. Okay, that makes life a lot easier for us. All right, because that's in meters, because that's in seconds. Let's turn that into meters per second. And I'll let you guys do that conversion, but I'll tell you what I got and you can compare it. I get that the velocity is actually 3.81 times 10 to the minus 11 meters per second. Okay? And now once I have that, the problem's easy, folks, right? I just know that omega is equal to V divided by R. Correct, right? That V, as we said, is 3.81 times 10 to the minus 11 meters per second. Okay? Divided by the radius, which is 55 meters. Okay? So omega is going to be 6.9 times 10 to the minus 13 radians per second. Tiny, 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 tiny amount, but nevertheless, this just goes to show you that every second, this tiny infinitesimal fraction of a radian is being moved, right? As this thing begins to fall. It's kind of interesting. Time has an ability to kind of trick us sometimes, right? Into thinking that, you know, things are frozen, things are not really moving, but sometimes it's just so slow that we can't see it. And that's the case with the Leaning Tower of Pisa. Okay? When we get back, we're going to talk about a few other rotational concepts, and I'll see you there.